So we'll start a discussion on today's lecture from the unit number 2, that is acid, bases and buffers. So now today we are going to start a discussion on buffer action and buffer capacity. Now what is the meaning of the word buffer action? Now buffer action is basically, it is a property of a buffer solution to resist the change in the pH value. See here, what is the meaning of the word buffer? The solution which will resist the change in the pH value is known as buffer. So that solution we are going to denote it as a buffer solution. But which property offers this, or which parameter is going to offer this property to that buffer solution? This is the due to buffer action. Now what is the meaning of the word buffer action? It is a particular phenomenon and process which is happening in that buffer solution which will not allow the change in the pH value of that solution. And the foremost reason for this to resist the change in the pH value of that buffer solution is due to the presence of common ion effect in that solution. Now here we have taken an example of acetic acid is a weak acid and its buffer solution. So the reaction responsible for maintenance of constant pH after addition of acid and a base in the buffer solution, this process is known as buffer action. So the buffer action of acetic acid and sodium acetate mixture, we are going to explain here now. Now we know acetic acid is weak acid. It is not going to completely dissociate in the water solution. So how much amount of ions of acetic acid will be dissociated? It is in this manner. Acetic acid is dissociated in water, in the acetate ion and hydronium ion. So this is an partial dissociation of acetic acid in water molecule. Now we have taken an acetate buffer in which there is presence of acetic acid and its salt containing common and conjugate base of the acetic acid. So we have taken an sodium acetate, which is a strong electrolyte, and it will completely dissociates in the water. So the ionization of this sodium acetate in the fractions, that is acetate ion and sodium ions. Now what happened later on? When a small amount or a few drops of acid solution we are going to add to this mixture containing acetate ions, hydronium ions, acetate ions and sodium ions. So this is a mixture, and in this mixture if we are going to add a small amount of acid to the above solution, the hydronium ion which are formed after the dissociation of acetate ions will combine with the acetate ions to form freely ionized acetic acid. So these acetate ions will react with the H plus ions, which is given by the dissociation of the hydronium ion. So again it will present, or again it will give the presence of acetic acid and water molecule. So the reverse of the reaction will be happening after the addition of acetate ions. See, we are going to add acetate ions, that means we are going to add H plus ions, and those are all H plus ions will react with the acetate molecule. So again we can generate acetic acid and water molecule. That means after the addition of acidic solution to the above mixture of acetate buffer solution, the pH remain constant, as it will result into again the formation of starting material. Now this is when we are going to add a acidic solution. Now when we are going to add a small amount of base solution in the mixture of acetate buffer. So when a small amount of base is added, that means OH minus ions are the base which will neutralize the acid molecules to form sodium acetate. So if we are going to add a base solution, so this base solution will neutralize this acetate ions which is formed after the dissociation of sodium acetate. So they will neutralize these acetate ions and form acetate ions and water molecules. They will neutralize these acetate ions to form sodium acetate. So therefore, again, there is the no net change in the pH value remains constant after the addition of small amount of either acid or a small amount of either base is added. Then also there is no any change in the pH value. This is due to the action of ionization pattern of that acetic acid and a if we are going to add small amount of acid or a base, and this is all due to the presence of common ion acetate ions in this reaction mixture, which will resist the change in the pH value. आणि या सर्व ऍक्शनला काय म्हणलं जातं किंवा या जी काही प्रोसेस हॅपनिंग होते, this all process is combinedly known as buffer action. Now we are moving towards the a discussion on buffer capacity. Now, what is the meaning of the word buffer capacity? Now, the buffer capacity is definition is it is the magnitude. Basically, buffer capacity is the it is quantitatively described by the buffer action. The magnitude of resistance of change in the pH value is known as buffer capacity. See, buffer action means कुठल्या प्रोसेसने they are going to stop the change in the pH value. That process is nothing but buffer action. And buffer capacity means किती अमाऊंटचं ऍसिड और अ बेस ऍड केल्यानंतर they are going to resist the change in the pH value. That magnitude, that quantity, that parameter is known as buffer capacity. So what is the meaning of the word buffer capacity? The magnitude of resistance of a buffer to change its pH value is known as buffer capacity, and it is denoted by the letter beta. It is also known as buffer efficiency, buffer index, and buffer value. See, buffer capacity have another 3 to 4 names. Buffer capacity is also known as buffer efficiency, buffer index, and buffer value. Now, the scientists Coppel, Spiro, and Weinstein introduced this concept of buffer capacity, which is defined as it is defined as the amount of acid or a base that must be added to the buffer solution to produce a unit change in pH value. So what is the definition? See, again I repeat my definition. It is defined as the amount of acid or a base that must be added to buffer to produce unit change in the pH value by 1. So, किती अमाऊंटचा ऍसिड और बेस आपल्याला ऍड करावा लागतोय if we are going to change the pH value of that buffer solution by only 1, either increase or decrease. So if we are going to add base, so it will increase the pH of the solution by 1. So either to change the pH value either by increasing side by 1 or by decreasing side to the 1, how much amount of acid or base is required to be added, that magnitude is known as buffer capacity. So I think I clear here. The magnitude of change in the resistance of pH value is known as buffer capacity, and a complete definition of buffer capacity is it is the amount of acid or a base which is added to change the pH value of buffer solution by a value 1. So by the present discussion, this is a formula for the calculation of buffer capacity. Beta is equal to delta B upon delta pH, where this delta B belongs to number of moles of acid or a base added to change the pH value by unit 1. So it is number of moles of acid or a base added to the 1 liter of the solution, and this delta pH is nothing but it is the how much amount of pH is to be changed. So this is a change in the pH value. So what is the formula for the calculation of buffer capacity? Amount of acid or a base added divided by how much amount of change in the pH value. This is a formula for the calculation of buffer capacity. So according to this equation, a buffer capacity of a solution has a value of 1 when the addition of 1 gram equivalent of strong acid or base added to the 1 liter of the buffer solution results in the change in the pH value by 1 unit. So this is a complete definition of buffer capacity. Now, buffer capacity is maximum when the concentration of weak acid and its salt or a weak base or its salt are equal. Then at that time, pH is equal to pKa or pOH is equal to pKb. So buffer capacity is always the change in the concentration of salt and its acid by addition of base are represented by using the modified Henderson-Hasselbalch equation for the calculation of buffer capacity. Now we know the Henderson-Hasselbalch equation for the calculation of pH value for the solution, not the buffer. But here, by slightly modifying the buffer equation towards the buffer capacity, what is the formula for the buffer capacity? pH is equal to pKa plus log of concentration of salt plus concentration of base divided by a concentration of acid minus concentration of base. Now, the capacity, that is buffer capacity, is not a fixed value for a given buffer system because it will change either by addition of acid or a base, but instead it is depending upon the amount of acid or a base added to it. So, uh, the buffer capacity always has a positive value. See here, this is always in a complete number and a positive value. However, addition of base increase the pH and addition of acid decreases the pH. Now we know when we are going to change the buffer of any system, pH of any buffer system, we have added either hydroxyl basic ions or acidic ions. So addition of base will increase the pH value and addition of acid will decrease the pH value. But the value of buffer capacity is always a complete number and a positive number. Now, this coming slide has given some of the examples of buffer capacity after addition of base or after addition of base. So, buffer capacity of solution containing equimolar amounts of 0.1 molar of acetic acid and sodium acetate. So, this is an acetate buffer concentration. How much there is change in the pH value. So, if we are going to add a 0 mole of sodium hydroxide in a solution of acetic acid, the pH is 4.60. So if we are going to increase the number of moles of sodium hydroxide, the buffer capacity will change slightly. So there are some of the buffer systems available physiologically in our body as well as pharmaceutically. Now, a blood, that is our connective tissue, is a very good example of maintaining the pH of our blood. Now, what are these ions which will maintain the pH of our blood? The plasma contains carbonic acid as well as presence of bicarbonate ion in our body is there, and a presence of acid and alkali salt solutions of the phosphoric acid and buffers. So our body has these many ions to maintain the pH of our blood system. Now our body also possesses plasma proteins which behave as a acid in the blood and can combine with a base so as to act as a buffers. Now, so our body has a presence of amino acid, presence of proteins, which will either give the acidic environment to the physiological solution as well as basic environment to these physiological solutions. So combined effect of all these ions, amino acids, proteins, lipids, acids, they are going to give the buffer solution. Now in case of RBCs, that is erythrocytes, the two buffer systems consist of hemoglobin and presence of oxyhemoglobin. Now we know our blood has a very important component, that is hemoglobin, and the function of this hemoglobin is to carry the oxygen and carbon dioxide towards the lung and throughout the body. So this combination of hemoglobin and oxyhemoglobin will have acid and will combine with acid and alkali potassium salts of phosphoric acid, so that the pH of RBC is also maintained at its constant level due to the presence of these hemoglobin and oxyhemoglobin. So these many buffer systems, beyond that also some of the buffer systems are available in our body to maintain the pH value, to maintain the body fluids pH value at their constant level. Now, some of the pharmaceutical buffers are also there. So buffer solutions are used frequently in the pharmaceutical practice. Why there is need to use buffer solutions in the pharmaceutical practice? Now pharmaceutically we are going to prepare the ophthalmic solutions. Ophthalmic solutions म्हणजे असे मेडिकामेंट की ज्यांची ट्रीटमेंट आय वरती केली जाते, EYEI. So we know eye is our delicate organ, and this organ is surrounded by so many delicate layers of the cell. So we have to maintain the pH value of these solutions. Then our blood, whose pH is always constant in between 7 to 7.4, so we have to maintain the pH values of these components. That's why buffer has its own importance in the pharmaceutical field. So buffer solutions are used frequently in the pharmaceutical practice, particularly in the formulation of ophthalmic solution. Generally त्यांचा यूज जास्त प्रमाणात कुठे केला जातो? ड्युरिंग द प्रिपरेशन ऑफ ऑप्थॅल्मिक सोल्युशन. कारण आय हा असा आपला ऑर्गन आहे की विच इज टू मच डेलिकेट अँड वी हॅव टू टेक अ कॉन्स्टंट observation towards the pH of the value. So one of the most important biological buffer is phosphate buffered saline solution. So this is a pharmaceutical buffer which is used widely for the maintenance of pH values of the pharmaceutical preparations, and the example of this buffer is phosphate buffer saline solution. Initially it is known as kiva, by short form it is known as PBS. What is PBS? Belongs to phosphate buffer saline solution, which is used widely for the preparation of ophthalmic solution to maintain the pH value of our eye and their semi-permeable membranes. Now, what are the components or contents of this phosphate buffer saline solution? It contains presence of sodium chloride, presence of dibase of sodium phosphate, also contain potassium chloride, monobasic potassium phosphate, calcium chloride, and magnesium sulfate. So these are all the salts molecule present in the above buffer system, that is phosphate buffer saline solution, to maintain the pH value, and this buffer is used widely for the preparation of pharmaceutical preparations. Now, what are the general characteristics of any buffer solution which we can use pharmaceutically for the preparation of buffer solutions? So, general procedure for the preparation of pharmaceutical buffers are: we are going to select a weak acid having its pKa approximately equal to the pH at which buffer is to be used. So, acid we are going to select की ज्याचा pH is equal to pKa. What is pH? pH is nothing but the negative logarithm to the base 10 of hydrogen ion concentration, and pKa is nothing but its dissociation constant. Now, we are going to select such a solution whose pH is equal to pKa, which can be used as a physiological buffer solution schema, which we can use as a pharmaceutical buffer solution. Now from the buffer equation, calculate the ratio of salt and its weak acid required to obtain the desired pH. So the buffer equation is satisfactory for the approximate calculation within a pH range of 4 to 10. So a sub acid or a salt solution, we are going to say select whose pH range must be between the 4 to 10. During selection of pharmaceutical buffer, we have to take attention towards the pH of the solution आणि त्याचा pH generally कुठून कुठेपर्यंत असला पाहिजे from 4 to 10. Then first parameter is pH is equal to pKa generally किंवा जवळ असले पाहिजेत एकमेकांच्या. Then their pH range is between 4 to 10. Then the third parameter is consider the individual concentration of buffer salt and acid needed to obtain a suitable buffer capacity. Third parameter for the selection of pharmaceutical buffer is consider the individual concentration of buffer. ज्यावेळी बफर आयोनाइज होईल त्यावेळी त्यांचं इंडिव्हिज्युअल कॉन्सन्ट्रेशन आणि किती अमाऊंटचं सोल्युशन रिक्वायर्ड लागेल टू obtain a suitable buffer capacity. So these are all the parameters of the selection parameters for the pharmaceutical buffer systems. Now other miscellaneous parameters for the selection of buffer is availability of the chemical. That pharmaceutical buffer whose chemicals किंवा ते प्रिपेअर करायला लागण्यासाठी जे केमिकल्स आहेत दे आर अवेलेबल. They must be too much available kiwa in wide quantity they must be available. Then sterility of the final solution. Sterility means free from microorganism, free from bacteria. So त्यांचा sterility proper किंवा sterility procedure must be smooth. We can sterile those products. So this is the next parameter. Then stability of the drug and buffer on aging. If we are going to store that buffer for prolonged period of time, it will not change their concentration or it will not change their pH value जरी आपण ते खूप दिवसांसाठी स्टोअर केलं then also. Then the cost of the material and free from toxicity. Last and very important parameter is the cost of the parameter. It must be cheap in the nature and they should not have any toxicity to the pharmaceutical preparation. So these are all important ideal characteristics while preparing ideal pharmaceutical buffer solutions. So these are all the characteristics of the buffer solutions. Now up till now we have seen that what are acid basis buffers, what is the meaning of the word buffer action, what is the meaning of the word buffer capacity, their calculations, their formulas, and their importance pharmaceutically point of view. Now here in coming slide we are going to see some of the importance of the buffer solutions. So buffer solution has its own importance in the biological processes. What is the importance of buffer solution in the biological process? The pH of the blood is maintained at its constant level, that is 7.4. This we have seen. Then in spite of various acids and bases produced in our body during the reactions like Krebs cycle, glycolysis, so many metabolism reactions are happening in our body which will change the pH value of blood. But this will not happen because due to the buffer nature of our body, due to the presence of bicarbonate and phosphate ions, they contain in our body too, which will resist the change in the pH value of our blood system. Now, buffer has its own importance in the industrial process also. So, what is the importance of buffer in the industrial process? The use of buffer is an important part of many industrial processes during the electroplating system. Now we know there is formation of so many semiconductor materials, so many electronic apparatus they are preparing. That time the pH of the solution and the pH of the plates are to be made constant. Now in the manufacturing of leather, in the manufacturing of photographic material, in the manufacturing of the dye, so these many industrial applications are also there with the buffer solution. Then buffer solution has its own importance in the analytical chemistry. For the some of the titrations, we have seen that we have started a discussion on the redox titration. We have seen the discussion on the complexometric titration. So that time, for the formation of a particular complex, the pH of the system must be maintained at its constant level. So during analytical chemistry also, uh, buffer solution has its own importance. Now we are moving towards a final role of buffer in the pharmacy. Now already we have seen some of the ideal characteristics of buffer solutions in the when we are going to prepare a buffer for the pharmaceutical importance point of view. Now, but this buffer has its own application in the pharmacy, as buffer plays an important role in the pharmaceutical preparations to ensure a stable pH condition for the preparation of ophthalmic formulations. Now, a pharmaceutical formulations intended for the application to the delicate membranes like eye, nose, alimentary canal. So they must be maintained the pH value adjusted to the same osmotic pressure. So we have to maintain the pH with that of the same osmotic pressure of the body fluids. So such preparations must be isotonic buffer solutions are used. Now, what is the meaning of the word isotonic buffer solutions? What is their role in our body that we are going to see? Now, what is the meaning of the word isotonic solutions? So these isotonic solutions are nothing but these isotonic solutions refers to the a solution having the same osmotic pressure across the semi-permeable membrane. Now, suppose we know these pharmaceutical preparations are used in the treatment of nasal tract infections, in the treatment of eye disorders, for the eye injury. So they must be isotonic with the semi-permeable membrane. What is the meaning of the word osmotic pressure? Osmotic pressure हे असं एक pressure आहे की it is the minimum pressure which need to be applied to a solution to prevent the inward flow of the water molecule across the semi-permeable membrane. Means this pressure is exerted by this semi-permeable membrane to stop the entry of water and other solutes across this membrane. And that pressure is exerted by this semi-permeable membrane. That pressure is known as osmotic pressure. That means this pressure is exerted by this membrane of that organ to resist the entry of water and other solute molecules across that membrane. This is known as osmotic pressure. Now, what is the meaning of the word tonicity? Tonicity is ability of extracellular fluid. आता आपण कुणाची ability बघितली? Ability of this membrane to resist the entry of water and other molecules inward to it. Then tonicity is the ability of this extracellular membrane किंवा extracellular solution to make the water move inside to the membrane. Osmotic pressure means pressure exerted by this wall to resist the entry of these molecules inside the membrane. Then tonicity means it is a ability of these extracellular molecules to make the water move in or out of the cell and cell by osmosis. That process of moving in and moving out by osmosis, this ability is known as tonicity. Don't confuse between the osmotic pressure and the tonicity. Tonicity is given by the extracellular fluid and osmosis is given by that semi-permeable membrane. Now, a solution must be isotonic with that semi-permeable membrane. That means isotonic solution refers to two solutions having the same osmotic pressures. Two solutions means सेलच्या बाहेर असणारं सोल्युशन as well as the solution which is inside the cell. Both have same osmotic pressure across the semi-permeable membrane. This state allows for the free movement of water molecule across the semi-permeable membrane. If the pressure on both the side is equal, that time water will move out and in of the cell. This state allows for the free movement of the water molecule across the membranes without changing the concentration of solute in either side of the membrane. So that time there will not be any change in the concentration of solute extracellularly as well as intracellularly. So this will happen due to the presence of same osmotic pressure across the semi-permeable membrane. So likewise, the pharmaceutical solutions that are made for the application of delicate organs and delicate membranes of the bloody fluid, so they must be isotonic with the bloody fluids. That means they can move out and in due to the same osmotic pressure with that of the membrane. So this is isotonic solution. When two solutions have same osmotic pressure and salt concentration are said to be isotonic. Isotonic means same concentration outside and inside the cell. So physiologically, isotonic solutions are solutions having the same osmotic pressure as that of the body fluid when separated by biological membrane. Biological fluid include blood and lacrimal fluids. Normally have the osmotic pressure. See, what is the normal osmotic pressure of the blood and our lacrimal fluids? It is approximately corresponding to the 0.9% W by V solution of the sodium chloride. 0.9% W by V solution of sodium chloride जेवढं काही concentration असतं, that same osmotic pressure is exerted by the blood and lacrimal fluids on their semi-permeable membrane. That's why 0.9% W by V solution of sodium chloride has essentially the same concentration and osmotic pressure to the RBC content. So it is said to be isotonic with the blood solution. That's why physiological saline solution, that's why it is known as physiological saline solution किंवा नॉर्मल सलाईन सोल्युशन. म्हणूनच 0.9% सोडियम क्लोराईड सोल्युशनला काय म्हटलं जातं? फिजियोलॉजिकल सलाईन सोल्युशन अँड normal saline solution. If RBCs are suspended in this solution, they undergo no change in their size and shape due to the isotonicity. That means 0.9% sodium chloride solution is isotonic with our blood as well as lacrimal fluids. That's why there will not be any change in the size of the RBC if it is suspended in the 0.9% sodium chloride solution. That means if it is suspended in the hypertonic solution and if it is suspended in the hypotonic solution, there will be the change in the size and shape of the RBC molecules will happen. This will discuss in the next class. Everybody